Hey guys,
Hello everyone.
I'm back. We have now we are Wednesday, January 10, and we are covering questions.
Monday.
Oh, is it already? Oh man. Monday, January 10, covering questions 20 and 21. So without further ado, let's get into it. Share my screen. Ooh, we got a lot of screens in this computer. There's this one. So starting with, whoops, I already clicked the wrong one. Starting with 20. I remember this one, trench map.
All right.
All right, so this one is considered an image enhancement algorithm where you start out with a field of, what are these, like light pixels and dark pixels, I guess, in a really crappy image that you've somehow taken.
Yeah.
In this very capricious submarine that sometimes does good things and sometimes does stupid things, but in this case, can't seem to enhance, so we have to help it enhance. But anyways, there's a algorithm to this enhancement. I don't remember exactly what it was, but
So you have to take the neighbors or the current pixel that you're examining and all of its neighbors, and you'll end up with
that's right.
you can from those nine points, you can create a binary string. You can create a binary number between 0 and 255, I believe.
Yeah, because the dot represents 0 and that
yeah, so the enhancement algorithm, you'll have to find the index of that binary number, and that'll tell you the result of what that pixel will be.
Okay. All right. So you're going to use those 9 characters, convert into binary, depending on whether it's a dot or a hash. Hash being 1, dot being 0. Convert that resulting 9-bit binary number into a decimal number, and use that decimal number to find the equivalent in this 512-bit field of equivalents, I guess, dots or hashes, to find out what it turns into, right?
Yeah.
We're going to do that through every field.
And it's supposed to happen simultaneously.
Yeah, and everything's supposed to happen simultaneously, so you don't like change one and then like use that result of one to work on the next one, and use that one as the result of that to work on the next one. Everything just kind of boom opens up. So there's some state management here, in other words, right? Because you have to hold the old states that can go back and reanalyze as you create the new state, which has the new characters in it. Because you're also working with neighbors, it looks like there's going to be some growth, right?
Yeah.
So the image itself is going to grow or enhance, as they say. Okay.
And yeah, one awesome thing about this one is that it's infinite size.
Yeah.
So you have to take into account that this will expand. Well, the size can be infinite. And for the sample, they made it a lot easier, where if it's surrounded by dots, like if it's only dots, then it will turn into a dot. But for the real input, it was not like that.
Yeah.
Right.
Which made it more fun.
Yeah, because with all of these, if you have 3, 3, and
0.
3, it's all zeros, right?
Yeah.
And all zeros on the sample image stays as dot. But I don't know, I guess a lot of ours, maybe everybody's, maybe not, but my first 0 was a hash.
Mine was too. I think probably all of them are.
Yeah, which made
it would be a lot easier if it wasn't like that.
Yeah.
And it would just make too much sense too.
I think, that's one of the things that I ended up struggling with, as the part of the challenge of this was like, how do I like flash all these things on and off? And I was like, oh, yeah, maybe I'll just do it even odds. But anyway, there are other ways I did it. But so the idea is to do this and to do it twice, apply the image enhancement algorithm twice, And then how many pixels are left lit? Ended up with 5,619. But of course, more interesting is the how. So who wants to start with the code?
I guess I usually go first with JavaScript, so I can start.
Cool.
Okay.
All right, you can see my screen now. And now you can see my code, right?
Yep.
All right, so this one's not too bad, a little bit messy. Let me first tell you how I decided to go about importing my data. So first of all, I just split the input, and then I shifted off the first row and called that my algo for my algorithm. So my algorithm's just that giant string of dots and hashes. And I'm going to use that later. Now I'm going to get my input. So first I had an empty element at the top of my input, so I shifted that off and got rid of it. Now my input is just an array of strings like this. But in order to handle the infinite size of the input or of the image, I decided to just add dots all around the image. So in order to do that, I added to every row first. So I looped through my input and I added, I think, 10 dots to the beginning of each row and 10 dots to the end. And after that, I created a string that just has a lot of dots. Well, each dot here is going to be the length of my new row in my input. And I added 10 of those to the top of my array and to the bottom of my array. So now I have a big array that's just this with a lot of dots all around it, just to help handle the infinite size part.
You missed a chance to make it 9, man. You should have made it 9 on top and 9 below.
Oh,
9 to the
man.
left.
Also 99. Yeah. Well, I did do something here. So my next thing let me talk about is my analyze pixel function, which I regret now because I should have named it check neighbors, because it's pretty much what I'm doing. And I've used that function so many times, I should have just stuck with it. So anyways, for my analyze pixel function, I'm passing in 3 arguments here. I'm passing in the current I value, which will be the row, the current J value, which will be the column, and then I'm passing in the array also. And with this, I'm going to check all the neighbors. So I tried to make it easy to understand here. I'm checking up left, up right, left, the current element, so the one in the middle, right, down left, down, and down right. And for these, I'm using optional chaining to make sure that that element exists before I try to get a subarray of it, so that I don't get an error. For example, if this I-1 array is undefined, I don't want to get an error here. So if it is there, I'm returning that I'm getting that element. If it's not there, I'm going to return a dot, which might not be the best for now, but I'll handle more in part 2. And now from that, now I should have all of my different elements as either a dot or a hash. So now I'm creating a string from that that'll give me my total. So I'm using a template string here to get my string in order. So up left, up right. This will be my 9-bit number. So I'm going to convert that to binary. So I'm using a regex replace to convert the dots to zeros and the hashes to ones. So now that I have a binary string, I can get the value of that from my algorithm, from my algo. So I'm going to pass in, so I'm going to return that value, my algo of index % of my total base 2. So that's the decimal of this binary string. So that's my index for my algo. So for example, if it's like 3, then it'll go 0, 1, 2, 3, and it would return a decimal or a dot. Any questions here? All right, so now what I need to do is I need to actually enhance my image. So I like to capture the length. So I got const D is my input length. And luckily, I think our input is a square. So we have the same number of rows and columns. So I'm going to loop through all of the rows and loop through all of the columns. And for this, I'm going to get the value that I need to insert, the value that I'm going to push in. So I created a new enhanced image, and I need to add in all of my values. So first I need to check if the row exists. Cool. If that row does not yet exist, I need to add in an empty array for that row. And then I will push the value into that row and into that column. Any questions? So my enhanced image is now the enhanced version. It's been enhanced one time. And I wanted to follow this, I kind of followed this question step by step. So I first enhanced it once, and then I wanted to check that out to make sure that it matched the input. So I joined it and console logged it, and it looked nice. So I went on and I made a doubly enhanced image. So my doubly enhanced image is just the same thing, except for this one, I passed in my enhanced image. And the result got into my doubly enhanced image. Now my doubly enhanced image, it looks a little bit extra large because it still has some extra elements around the top and bottom and sides. So just to clean it up a little bit, I shifted those off. So I shifted off the tops and popped off the bottoms. And I did the same thing for the sides, just getting rid of the extra elements that I had added at the tops and sides. And now all I have to do is count how many hashes I have in my doubly enhanced image. So I just loop through here. I search anytime I find a hash. I'm going to increase my counter. And then all I have to do is return my count.
Cool.
Any parts you want to see more? Was it similar to yours, maybe, but less clean?
Well, you're 46 to 54, since you're there anyway.
Yeah.
If you're going to use a ternary operator, why not just put the ones and zeros right in there? Instead of doing to the replace on 58, 59.
Yeah, good idea.
But if you do want to use
Yeah.
the null check,
For these ones, I don't know, but yeah, for here, yeah, I could just do all the dots instead of dots, all these zeros.
for the null checks, you can
Yeah.
actually do, there's a null, or I think JavaScript calls it a null-ish coalescing operator. They'll save you a couple, well, it's about half the length of the line. Basically, you do the evaluation of, just like you're doing here, whether or not a certain thing exists, the variable exists, and if it doesn't exist, you can actually, through 2 question marks, pass in a default value. This is essentially what you're doing.
So then it'd just be like this?
Yeah.
That looks a lot cleaner. Okay. All right, nice. Or, so I could just pass in 0 here.
Yeah, all the dots are up into zeros, and then you can comment out 58.
I think I still need that one though, in case these values end up being dots.
Ah, that's true.
So,
Including the current.
yeah. Yeah, so I still need 58 and 59.
Yep, yep. Cool.
Yeah, that's clean. Thank you. All right. We see someone else's?
Who wants to go next? Python? Oh, you're muted, buddy. Oh, and you're frozen.
Oh no, Farouk, you're on mute.
Oh, there you go.
Can you hear me?
Yep.
Okay, we got it.
Okay. Share. Okay. So, can you guys see my screen?
Yep.
Yep.
Okay. So my logic is that first I'm splitting my algorithm with my input. And then before I start working on my input, before I start calculating my new board, I'm adding a layer to my already existing image. And also I'm storing my input image as a dictionary. So I also again have the indices as the dictionary keys, and I have the value for that index represented by 0 or 1 as a value for that dictionary. So indices are the dictionary keys and values are dictionary values of this my image. So after I add a layer, I will run the logic, which is represented in the question, to get my new board. And before actually I get my new board, I will also determine my surrounding layer to represent the infinity of the image. So if my 0 index is dot, my surrounding image is actually always 0, which means that's also dot. And when it's hash, my surrounding image will be the opposite of it. So if it's dot, it will be a hash, I think. And if it is a hash, it will be a dot. See, surrounding. Okay. So first, I'm reading my input here. This is the start. I decided to do it in a separate file since it was a really big input. So reading my lines, dividing it, and storing my image here and my algorithm here as a single string. And I'm converting my algorithm to 0 and 1 rather than keeping them as hash and dots with this line. So now I have my image input stored in image variable, and I have my key stored in I have my algorithm stored in this key variable. So next, I'm going to convert my image to a dictionary. So my new dictionary, and instead of using range as before, I'm using enumerate here since it's directly giving me the values and the key counter for that value. So I'm storing the hash as 1 and dot as 0 in my dictionary. So at this point, I have all my indices and the values for that indices inside this dictionary. And after that, I have my for loop to apply my enhancement algorithm as many times as I want. So first, before starting my enhancement algorithm, I'm deciding what will be the surrounding layer will be for my input. So to get that, I'm using this logic. So I have my first index element in my algorithm. If it's equal to 1, which means it's a hash, the filling layer will be it will be reversed basically. 1 will be converted to 0 and 0 to 1. Otherwise, the surrounding layer will remain on 0. This logic. So I'm adding 2 layers to my board. Is my add layer method. So first I'm getting the bounds or the edges of my board so that I can start adding the layer, surrounding layer to my board. So in that get bound, I have the minimum and maximum elements. So if I have a minimum index in my dictionary, which is less than the minimum number in Python, or if I have the larger index than the first, I'm setting them to the most smallest and the largest numbers. So as I go, I'm assigning the minimum value to xmin in my board. So it will return the edges of my board. And once I get the edges, yeah, I will get one less and one larger indices for my board. And then I will add those to my board. Here I have my indexes. So I have my starting index and ending index, which is in this range, x1 and x2. And for the y direction, also same way, I'm adding another layer, starting from the bound of my board. So I have a larger board to count for the infinity of the image now. It's basically what Scott did, but he was doing it with the strings. You are adding the dots, but I'm doing it with the indexes. So once I add my layers, I will get my bounds one more time with my get bounds or get edges function. So, and after I get my bounds, I have to get, since this range is exclusive, I have to get one more plus to get the latest edge bound 2. And after that, I have a new dictionary to represent a new board. And I start looping through my existing indices. So these are the indices of my board. I will start looping through this range. And every time I get a certain indices, I get the decimal value for that indices. So now I have this J and I represents the middle point in that 3 to 3 grid. And if I call my get decimal value function, I have already the range for my 3 to 3 board. Based on the index I'm passing, I can detect like my y1 from y minus 0 to y plus 2 and x minus 1 to x plus 2. I can get all the points that 3 to 3 grid. And I'll get the new indexes, get the value for my board that corresponds to those indexes, and store them in my string, which represents the binary. And I will return the decimal value for that binary and assign that new value to my new board in this corresponding indexes. And I'll call my loop as many number of times. I think working with dictionary as index and values help me to as a frequency counter approach, because it doesn't get, since I have my bounds and my board, I don't have to worry about the string or how it will, how to manipulate a string.
Can you repeat that last part? Because you have bounds, you don't need to do what?
So if I have it as a string, I have to get my bounds anyways, edges, right?
Right.
But if we already have it as a dictionary indexes values, I don't have to recalculate, or I don't have to calculate it at all.
Okay. So you're saying it's included in your normal calculations, right?
Yeah.
Cool.
Nicely done.
Any questions?
No. I think for part one, we pretty much all kind of followed the
Directions.
the instructions as it was. There's nothing really fancy yet.
Yeah.
Okay. So now I'll stop sharing my screen.
Okay. I'll move on to the rest one. Let's see, where am I? This code. So for mine, today. Yeah, reading from a file. Looks like I get, just like you guys, I separate what's considered the algo line versus the actual input. I have a couple functions here. Can you see this? Do I need to be bigger?
A little bigger would be nice. That's good.
So we have an expand function, which essentially just adds padding to grow into, as it says, so just like you guys, add a little bit of padding. Necessary because in order for us to get the dots, right, we need to, it's always going to consider an infinite number of dots. And if it's always 0, that's, that's not a problem. It's always going to be dot. But then like you get into a situation where you have dot, 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 and then you have something in the corner like a hash, then that middle one is going to change. So you're always going to have at least a border of 1. You can even probably push it out 2, but realistically, you should push it out at least 2, I guess, if you don't want to do any recalculations.
Yeah, I think at least 2 on each side for every step.
Yeah.
To be safe.
Anyhow, so we also have another function called get neighbors. Get neighbors just gets all the neighbors as binaries and compiles it all together into a binary, a binary string. String being the keyword. I have a print grid, which I don't use just for pretty printing and for decoding. And then I have a cycle, which runs a cycle of the enhance. And then, so hacky fake border. So I expand it at least 20 in each direction. So 20 on top, 20 to the left, 20 to the right, 20 to the bottom. But from my testing, it seemed I needed at least a 3-character gap instead of a 2-character gap. But anyways, I provided a 20-character gap. I run the cycle twice. And then I go in and I count the hashes. That's about it. So let's take a look real quick at the expand function. Expand function essentially just pushes to the front and the back of each line and then adds also the dots to the top and bottom of every line, just like you guys had done. Only difference is I guess I can pass in however many I want. And the get neighbors function, I think it's nothing elaborate, just getting the stuff above in the rows, below in the rows, or above and below in the rows, and then on the actual row itself on the columns, and then just getting whatever we need. I don't know how deeply you want to get into this because it's Rust. But essentially that's all it's doing. So I get a row from 0 to 3, I subtract 1, which actually means it's going from 0 to, well, this is actually 0 to 2, right? Because it's not inclusive. I could have put it equals 2. Maybe that would have made it a little bit little bit more clearer. Because then it's 0 to 2, and then you subtract 1 from that. Now it's -1 to 1. That's essentially the idea here. And same thing with the rows. It's -1 to 1 after I do the subtraction of 1, and then I get those -1 to 1s. That'll get the one to the left and one to the right and one to the right above me, and then the same with my row and the same with the row beneath. And that's it. That's pretty much it. The cycle function, just like you guys, go into every row, every column, get all the neighbors, convert all the neighbors to a number, and then turn them all using the algo into the character that's appropriate, and then creating a new vector with the appropriate characters that are coming out.
Cool.
Cool. The only particularly maybe interesting is I used a DQ vector, which something I started using somewhere in the middle of Advent of Code, so that I can have an efficient way of pushing things to the front and the back without having the entire array having to shift in memory. So, but that was just a small enhancement, a small performance enhancement. But that's about it. That's my code.
Let's go part 2.
Yeah, let's go part 2. So part 2, let's see, going back to
Enhance it 50 times more.
yeah,
Same
50
thing.
more times.
Enhance, enhance, enhance. 50 times.
So if at all you are a little bit off on any of your borders or anything like that, your puzzle gets kind of awkward. So does your results. But I think for mine, I didn't really have to change much, I don't think. Let me see what I remembered. I think the
Yeah, equals 2.
What's that?
Equals 2 to equals 50 maybe?
Yeah, except that, because I'm sure your guys too, the inputs that I got, let's see, that was 20 in. So 0, 0, 0, 0, 0, the 9 zeros turn into what used to be a dot turns into a hash.
Yeah.
And then what used to be a hash turns into a dot.
Yeah.
So
it just alternates.
512 turns into a dot, right? Because it's all hashes. So basically the whole thing like flashes.
Yeah.
All the infinite space that used to be a dot now it goes to hashes. So all the infinite space that used to be a hash goes to dots. So everything along the borders gets a little bit wonky if you don't have the right algorithm for the borders. But anyway, I think for mine, I don't think I changed anything else. Let's see. Still have expand. Oh, I even tried like creating a function called reduce, because remember those 20 things I added, the 20 border I added? I created a function to strip out those 20, but I ended up not using it because I think what happened is in the expand itself, I made it a little bit smarter. It gets to whatever the current border character is. So I mean, if it's currently the negative space should be hashes, then it creates hashes. If the negative space should be dots, it creates dots. There's a little bit more intelligence there. I could just, I don't know, because of the dot. But then the get neighbors, I guess the get neighbors is a little bit smarter. It looks a little bit different. Deal with space beyond current grid borders. First row doesn't have the row above it. It's just whatever the character is infinite. Oh, so I think I created the second version with, yeah, without the expansion, the pre-expansion of characters. You'll notice that I don't have any expands before I start. Oh, I have expand only on the cycle. So it's not like some weird number of expands. I just have it expand itself, and it expands appropriately to the size that it needs. But I also have to take into account then if it goes beyond the certain borders, what do I need to do? But that's about it. Other than that, other than to kind of clean up the way that the borders are generated and dealt with. I think the rest of the algorithm is the same. Yeah.
Cool. Yeah, not much different from part one.
What's that?
Not much different from part one.
No, not much different from part one. Other than the a little bit cleaner way of dealing with the borders. I just pushed the number of cycles from 2 to 50. Yeah.
All right.
Cool.
Let's see, JavaScript or Python?
You can go first. Mine is basically the same.
Okay, I'll go then. Let me share. Yeah, I'll just share my desktop. All right, can you guys see my part two? All right, so my part two, I didn't make it that much smarter. I was getting a lot of wonky things around the borders. So my quick and easy solution was to just expand it more, just add more space around the edges and then crop that at the end. So instead of adding like 10 or 20 to the beginning, I added a lot to the beginning and end. I think I added, yeah, like 60 extra to the beginning of each row and 60 extra to the end. These ones I just played around with to get it not too big, but to look a little bit cleaner, but still be big enough to get accurate results. I added, yeah, 60 extra rows to the top and bottom. And then, yeah, my analyze pixel function is essentially the same here, except there's one small difference. So now I'm going to be running with two different arrays. I'm going to be alternating between my input array and my enhanced image array. And to start out, my enhanced image array is just a copy of my input. So yeah, with JSON parse, JSON stringify, I made a copy of my input array, and I'm going to use that. So now with my analyze pixel function, I'm going to pass in two arrays. I'm going to pass in the in array and the out array. The in array will be the current image, and the out array will be the enhanced image. Because I don't want to modify the in array as I'm going through it. I just want to push things to the out array. And I also added in a border element here that I'm going to use to kind of try to keep track of what the border elements should be based on the infinite image. So similar to what Alex did, but maybe a little less smart. But yeah, other than that, my logic is essentially the exact same, except a little bit cleaner, because now instead of doing my enhanced image and my doubly enhanced image, I'm just gonna use my main loop here to alternate between what is my image and what is my output image. So I'm gonna keep track of my K value. So that's gonna be what cycle I'm on. So if my K modulo 2 is equal to 0, then I'm going to call my analyze pixel function. I'm going to pass in my input array as the current image to be enhanced, and the enhanced image will be the output. But otherwise, I'm going to pass in the enhanced image as the input and input as the output. Input as the output. That sounds confusing. And also, I'm going to pass in my border. So if K modulo 2 is 0, then I'm going to pass in a dot as my border elements, or else I'm going to pass in a hash as the border elements, because the dots and hashes will just flash on and off. All right. And yeah, so that ended up being all that it took. Now we just got to count the hashes. And this is what my map ended up looking at. Like, can you see my terminal here? Yeah, so I was able to see my giant, ugly map. And apparently this is useful somehow to Santa's elves. Yeah, I don't know what this is supposed to be. I guess it's supposed to be the trench, right?
I think I see the key in there, man.
Huh?
I think I see the key.
Yeah, I don't know, man. All the way at the bottom, like down here? I don't know. Very useless map, I think.
Okay, I will share my screen. The problem was the extension of the edges, since it's different on every loop. Since I was recalculating the layer edges every time I enhance my image, the bounds is being recalculated. So the higher number of loops, I think, did not cause a problem, since the edges are being recalculated on every run in my algorithm. So just updated the 2 to 50. It took a longer time, but gives the correct answer.
How long did it take?
10 seconds
Oh.
or more.
Oh.
No, it wasn't more than 10. Yeah. So maybe 10, 15.
Okay. I didn't use a timer on my code, but just roughly estimated mine was like 3 seconds, maybe. It's lower than part 1 for sure.
So yeah, around 10, 15 seconds.
No, I think that's right around 10.
Cool.
So that's the only update I did.
Nice. Just change one line, one number.
And the rest is same, yeah.
All right.
Cool.
Yeah, this one, if you get part 1, part 2 wasn't that much harder, I think. Mine took a little trial and error, but not much.
Okay.
All
21.
right, let's go 21.
21. I enjoyed 21. I thought it was a fun one.
The part 2 was torturing me, the 21.
Part 2, yeah, you had to think, I think, to find the patterns. At least I did. I used a pen and paper for a while on part 2.
And for a while, and then what happened?
Then I saw some patterns and I jumped into the code. My part 2 ended up actually looking at so much cleaner than my part 1. Because my part 1, I just made the game.
Right, brute forced it.
Yeah.
Okay, so basically you have some deterministic die that always roll, between 1 and 100. So 1 and then 2 and then 3 and then 4 and so on. At each turn, each person gets 3 rolls and adds up those rolls to determine how far they go on a board with spaces that only go from 1 to 10 and then roll back around.
Yeah, just a circular board.
And the space that you land on determines the amount of points you get. And they want you to stop after you get how many?
1,000? I think it was 1,000 points.
Okay, 1,000 points. So as soon as anybody gets 1,000 points, you stop. But then the question actually is, what do you get if you multiply the score of the losing player by the number of times the die was rolled during the game? So you have to keep track of how many times the die was rolled, as well as the score of the winner to know when to stop, and the score of the loser to know how much to multiply for the final answer.
All right. And each player gets their own random starting position too.
That's right.
So that's actually going to be your input, is the different starting positions.
Yep.
All right. Shall I go first?
Sure.
Okay.
All right. For this one, I tried to just follow the directions as closely as possible. I tried to just make the game. So since the input was so short, I just brought it into here as my input. I started with my player 1. I created an object for const player 1. I'm going to keep track of his position. My player started on position 10, and he's going to start with a score of 0. Likewise, my player 2 started with a score of 0, but he's on position 4. Now I'm going to create 2 variables here. My die is currently on 0 because nobody's rolled it yet. And my number of rolls, I'm going to keep track of how many rolls have been used, is starting at 0. So now I create a couple of functions here. The first function I created was roll. So every time someone rolls the die, I'm going to run this function. And it's very simple. I'm just going to increase my die counter and increase my rolls counter. And then I have an extra check here to check my die. If it's greater than 100, then I'm going to drop it back down to 1. And I'm going to return the value of my die. So not too complicated on that one, I think. My next function here is to play the game. So in here, I accept 2 arguments, the current player, that's whose turn it is, and I'm also going to accept the loser. And this is mostly just for printing out the final answer later. It's not going to be used until the very end. So when the game is played, I'm going to roll 3 times, and I'm going to track those. I'm going to get roll 1 is, the return value of this roll, roll 2, and roll 3. And then I'm going to sum all of those rolls, roll 1, 2, and 3. Next, I'm going to check how many times does that player have to move, because the move is going to be equal to the roll sum, but I don't want to be moving like 75 times. So I'm going to modulo 10 the roll sum, and that'll give me how many times I have to move. So I'll just pretty much cut off, if, for example, if it's 75, I'm going to cut off the 70 and just take the 5, because that's all that matters on my circular board. Next, I have to find where is the player's new position. So I'm going to check if my player position plus moves is greater than 10. That means that I've gone a complete circle. Then I'm going to do the same thing as I did up here, is I'm going to do a modulo 10 of player position plus moves to cut off the 10. And I'm going to set that to my new player position. If this player position plus moves is less than 10, then I'm just going to set that to my new player position. Okay.
Well, kind of unnecessary, because you could do modulo 10 on both.
Yeah, I could. Yeah.
That
was logic added later that, yeah, definitely could have been cleaned up more. Thank you. All right, now I'm going to add to my player score. My player score is going to add the new player position. So now I just have a check if my player score is greater than 999. So if it's 1,000 or more, then I have a winner. So I'm going to console log my loser's score times the number of rolls. That's the only reason I'm passing in loser, is just so I can get the score of that player. So now my main loop here is I'm just running a while loop. While both players' scores are less than 1,000, I'm going to play the game. First, I'm going to start with player 1's turn, and then I'm going to do player 2's turn.
Cool.
Not too bad. Pretty much just followed the instructions as best I could.
Question number 1. I mean,
It's short and simple, right?
Like a 21.
Yeah, but it's going to be even shorter if I take out the sample info here. It's what, 43 lines?
So what's the question? Part 2.
Yeah, not much for that one. Part 2 then. Oh, this one was a great advent of code question where they kind of deceive you on part 1. They're like, oh, here's a nice question, and it's seriously like day 3 difficulty.
Yeah, that's what.
And then part 2, you read and you're just like, brain explodes even trying to figure out what the question is.
Okay, so Python. Yeah, not much different from you guys. Much for part 1, following the instructions. So I have this practice dice function, and I'm reading my input txt or sample inputs, which is just 2 digits, and calling my practice dice function. So first I'll get my positions for player 1 and player 2, initializing the scores at 0 for both players. And I have a variable for rolling dice and number of rolls. Rolling dice. Yeah, I think it's the count. So I have two Boolean values for the turn too, which player turn it is now. So I have a while loop until scores are less than 1,000. I have a step. So for this range, I'm my number of falls, I'm incrementing my dice number and getting my current steps. Yeah, how many steps the player will move. If it reaches 100, I'm setting it back to 0. So if it's player one's turn, I move player one's position. First, I'll get my landing positions, like how many positions player one needs to move, and then add it to my player one position. So if it's higher than, if it's 10, if the modulus remainder is 10, it's at 10. Otherwise, if it's a remainder, I think. Otherwise, it's set to the remainder of modulus 10. And I increment the score by the new position. Same logic for player 2 here. So, and then I will toggle my turns. I will toggle the turns this based on this logic, and I will calculate my loser player score, the score of the user, and return the number false by, can multiply it by the loser player score.
All right.
All right. So you have two Booleans for player one and player two turn. Is there any point in time where the two can be the same?
Maybe not. I think not. Yeah.
Where's
This
the,
one maybe can.
Where's the check?
So I can actually remove player 2 and get the player 1 opposite of player 1.
Yeah.
And remove this one. Next.
Then
No.
So you have your dice go from 0 to 999. So that's how you dealt with.
Yeah. So does that work?
The difference between, the way the programs count from 0 to 9 versus what the playing board had 1 through 10, right?
Mm-hmm.
And so you decrement the spaces from the die to make sure the two match up.
Sorry, can you repeat the question? I was checking the answer if they match.
Oh, okay. The one of the kind of, I don't say a challenge, but the gotchas on this one is that the board goes from 0 to 10, not 0 to 1 through 10.
Yeah.
Right. But if we want to use a modulo, the modulo goes from 0 to the 1 less than the modulo number.
Mm-hmm.
So for modulo 10, it goes from 0 to 9. Right.
Yeah.
And then from that 0 to 9, we're trying to figure out the moves, right? Because it gives us a moves value. But the moves value is based on because it's for example, let's say we want to move forward 5, but our original position was 1. Now, if you had the original die from 1 through 100, you would actually have gotten 6 instead of 5. So they would have moved to 7. But because the die goes from 0 to 99, you only go for 5 moves. And so that's how you compensate for that modulo difference.
Mm-hmm.
Anyway, That's one of the gotchas, and I thought on this one is that there's a discrepancy when you want to use modulo, but you're limited to 0 through 9. So you have one compensating line where if the modulo is 0, then you say 10. And the other compensating thing is the rolling of the die, since you're rolling 0 through 99 instead of 1 through 100. It's cool.
Okay.
Cool. Hey, Scott, what was your starting positions?
10 and 4.
No, so all three of us got different inputs.
Okay. Interesting.
6, 9.
Wow. Alrighty. Is that making sense, Alexi?
Yeah.
This one seemed a lot simpler.
Yeah,
At least
that's
part 1.
what I was saying. The Scott, it looks like question number 3. I didn't look at it yet, but I mean, I didn't look after question 10. So every time what you're talking to.
Actually, my part 2 is even less code, but way more brain explosions.
Can we cover part 2, or did we already do it? The question?
No, we haven't started.
Alex is going to be part 1.
Yeah. So my part one is pretty small. I have a lot of comments, but it's probably only 30 lines, if that, maybe 20 lines. I don't know. So my starting lines were different. It was the opposite of the demo. Instead of 4 to 8, mine was 8, 4. I have a function for rolling the die too, but to kind of speed things along, I roll all 3 die, and then I return all 3 die at the same time, the sum of all 3 die. Players, I have just a vector of player 1, but I use a -1 to compensate for the way the board is geared versus the way that I treat numbers. And so I start 1 less than the actual starting number, so that my board then logically it goes from 0 through 9 instead of 1 through 10 to just keep things on the same kind of number scale for everything that's going on. So other than that, I have, two variables, just like you guys did, to get the current state of the die and the number of turns, or the number of dice rolls. I determined who was going to go just by even or odd numbers. So depending on whether my loop is running in an even or an odd, that dictates whether it's the first player's turns or the second player's turn, just by with the turner or the modulo 2, then I know whose turn it is. And every turn I get the next roll, move the spaces, increment the points, turn +1, next thing goes around. Now modulo 2 is the opposite. So then the other player goes and does his thing, and then so on and so forth, all the way until max score, which in this case was 1,000. And then we just print out the math that we need, the losing score times dice rolls.
If you got rid of all those comments, your code is super short, like 25 lines.
Yeah, it was, when I first wrote it, I actually even had all these, but I was able to reduce those lines. I had it, turn 1 and turn 2, each player specifically.
Yeah.
There was a lot of copy paste between the two. So I was like, oh, I could probably reduce that down. I had a little bit of time left in the kink, and I got this done quick. So that shrunk down to these lines, though it doesn't really look like I shrunk more, because all I did was displace that with, I don't know, maybe I saved 2 lines. But also, as I said, academic, probably not more readable. Essentially, I changed it with a reference, depending on whether or not it's an even or odd number.
Okay.
Anyway, that's
Cool.
fine. So let's go
Part
part
2.
2. Yeah.
Oh, this is a good question.
So let's go take a look at part 2. So part 2, we've changed our
Reference time is finished.
what do you call it? The
Deterministic
die with the quantum die. And so this one, in the spirit of quantum, all 3 exist at the same time, right? So we got to figure out, and as you roll this die and 3 realities appear, each branch out into their own universe, where you can have 3 more rolls of the next player, and those branch out into 3 universes, and then so on and so forth. So you got all this entire idea of probability and everything. But in the end of it, they want you to know in how many universes, find the player that wins in the more universes, and how many universes does that player win? And it's a very large number.
And I can see your answer there is a gigantic number. What is it? Something quadrillion?
So there's the
100,000 million. Those are billions. Oh, it's only 4.5 trillion, looks like.
Yeah, about 4.5 trillion. So, but anyhow, the old version of like what we did in our last code, where we just bumped the number from 2 to 50, it's not quite going to cut it in this one.
No.
So I'll start with, I'll just start with mine since I'm already projecting. So mine, let's see, I had to change, obviously, the way I approach this problem. Oh, I think I have it in here in my little graveyard. I first try to combine the deterministic die to see how many possible rolls and roll combinations there was, and how many turns I would have to do those roll combinations. And so I found it probably between 10 and 11 turns max before there was a winner. But other than that, that old way of doing things was not going to work. So I went back and re-engineered the solution. So I still have, I still use the probabilities of the basically combos. What I decided to do here was frequency counting. But to do the frequency counting was done by dice rolls. So I knew that for every dice roll, there is one combination to roll a 3, which is a 1, 1, and 1. 3 combinations to roll a 4, 1, 1, 2, 1, 2, 1, 2, 1, 1, and so on and so forth, for all the different possible rolls. So the first number is the number that appears in the die, the total number that appears in the die. And the second number is how many times or how many combinations of die can appear that way. Then I basically...
That was the main key to this problem too.
What's that?
That was the key to this problem, is finding the probabilities of each roll.
Yeah, I think so.
I know I ended up having that in mind too. That was the key that allowed you to cut down the probabilities.
You got to do stuff, right? Because you just multiply by the possible occurrences rather than, playing each one out individually.
Yeah. And that allows you to cut every branch from 27 new branches into 7 new branches.
And so, other than that, I mean, I do keep track of various possible states, and the various possible states depend on, where the characters are at a certain point and whose turn it is. And if the state has already been done before, if some other way they've been able to get to this particular position where character 1 or player 1 is on, space X, and character 2 or player 2 is on space Y, they're still going to roll the same 3 dice, right, every time. And it's going to be 1, 2, 3 every time. And so there's no point in re-simulating that. And so I cache positions and players where they are to not have to re-simulate that branch. And so I create a little cache, and then if this particular combination of where player 1 is and where player 2 is and whose turn it is, if that combination already comes up again in the future, then I don't replay it. I just read it from the cache because I know what are the possible outcomes from that branch of possibilities. And so that also cuts down a lot of unnecessary churning on the computer.
Yeah.
That's pretty much my 2 optimizations: optimizing by caching branches on possibilities, and pre-loading all the possibilities so that later on I could just multiply by the number of possibilities rather than playing out every single possibility of the rolls. And that's pretty much what it does.
All right. Cool.
All right. Who wants to go next?
You want to go first this time, Farouk?
Okay. So I also reworked my logic for part 2 because why not?
Because you had to.
Okay. So my approach is also different, totally different actually in my part 1. I also keeping track, not the index and the number of possible combinations. It's storing the number possible states as a position 1, position 2, and the scores too, because scores also cannot overgo 21, right? So I have a play quantum dice which will take my positions -1. I am taking positions -1, and the initial scores. And I have a possible states dictionary that will keep track of all the possible states because it's limited. I'm not pre-populating this dictionary. I'm creating it as I go. So I'm keeping track of the state once the game ends. Actually, no, not once game ends. As they go every time, I'm keeping the possible states, position 1, position 2, and score 1, score 2 in a dictionary. So when I come to the function next time, if these positions and scores exist in my dictionary, I'm using that value. So that's the, I think, key I had here. If the scores go over 21, I'm returning 1 and 0 and 0, 1 and 0 and 0, 1 in my recursive function. And if my positions and scores exist in my dictionary, I'm returning that value instead of going down to my dictionary. Otherwise, I'm calculating the answers for 3 possible states in 3 different ways, combinations. I will get my point, new score for that point, and call my same play quantum dice one more time with the new points, new positions, and new score. And store the answer or calculate the answer by adding the values of y1 and x1 from quantum dice. I will calculate my current answer points and add that to my dictionary. Yeah, that's the approach I took to eliminate the possibility of going many possible combinations in that quantum universe.
How do you determine whose turn it is?
So every time I'm passing the positions. I think turn doesn't matter in this one, since answer is already in the dictionary. No matter whose turn it is, I can get the answer from that dictionary if it's already there, based on the point.
I think for whatever reason with mine, I actually had to include, like you, I included the positions and I included the scores, but I also had to include whose turn it was. in order to get the
But
right answer.
you didn't have the score in your dictionary, did you? Like you had the number of possibilities, no?
No, I had the position, I had the space that they were on the board, and I actually had the score. I didn't actually say it, but I also had the score. So I have those two. And then I left it that way for a while, but I kept generating the wrong answer. I went back and on a whim, I decided, all right, maybe the turn matters. And I added the turn in, and then I got the right answer. But I don't know, maybe you got.
I'm not storing the turn.
Interesting.
I'm just using positions and the corresponding scores for those positions
Okay.
for both players. Yeah.
Yeah, I guess, the end, they could be determined separately because one doesn't affect where the other one is. It's not like you can't jump over the other person or you can't occupy the same space. So
There's no rules like that.
yeah, so you could calculate them separately. Interesting. I don't know. For mine, for some reason, I understood that you could do them separately, but for some reason, and that's why originally I didn't have the turn in there because I thought it was independent, but for some reason mine didn't get the right answer. I still don't really know why.
You do have to do them in order though. Like if you do player one and then player two.
Right. No, don't know. Cool. I mean, it worked for you, so just trying to figure out like where the turns got into mine, because yours doesn't. Anyway, cool, man.
Good job.
Are you also scoring the scores for both players?
Yeah, the data structure I have is a single data structure that contains a vector that contains the position and the score for every player. And then I put it into a state cache that is indexed by whose turn it is, a 1 or a 0. And so it has to match that entire thing. It has to be not only the same position and the same score, but I had to also match it against whose turn it was to make it work for mine. Don't know.
Okay.
Anyway.
Let me share mine.
Yeah.
Where did it go? There it is. All right. So mine is a little bit messy, but compared to your guys, it's a little bit weird and repetitive, but I like the way it works because I feel like it follows the game logic quite well. So let me talk. The first thing I did is I wanted to be able to go around my board without having to loop around. So I created a board array that just goes from 0 to 10, and then it starts at 1 again and goes up to 9. So this way, if I'm at like, for example, 8, and I add 9 to it, I can just go plus 1, 2, 3, 4, 5, 6, 7, 8, 9. And okay, now my final result is a 7. So it'll come into play a little bit later. And now my initial variables are just going to be player 1 wins and player 2 wins, and I'm going to track those. So now all I have is a recursive function called play game. And I'm keeping track of more state variables than you guys even. I'm keeping track of player 1's score, player 1's position, player 2's score, player 2 position, and I'm also keeping track of whose turn it is, and the multiplier. So this multiplier is going to be, like Alex mentioned earlier, the probability of a certain roll occurring. So for example, 3 means there's only one possible option. But for example, 6 has 7 possible ways that you can roll a 6 with 3 dice. So now I actually decided to do some weird stuff where at the beginning of each roll, I'm going to add to the other player's score. So because of the way my logic works, for example, if it's player two's turn, I'm gonna, at the beginning of player two's turn, I'm gonna add player one's new score. So I just have a check here for checking whose turn it is. If it's player one's turn, I'm gonna add player two's position to his current score. And then I'm gonna check if he wins. If he wins, I'm gonna add to his win variable and I'm gonna return. Same thing down here. If it's player two's turn, then I'm gonna increase player one's score and check if he won. Or she, maybe it's a girl, I don't know. And now, if it's still player one's turn, I'm gonna play my game and I'm gonna do my recursive function with my new states. So player one's score is gonna stay the same, but my board now, so my position is gonna be based on my board. I'm gonna pass in the current position plus the roll that he got. So this, if I add 3, that means that was he rolled 1 and then a 1 and then a 1. And so I'm gonna check his new position on my board, which is up here. So for example, if he was at 3 and he rolled 3, go 1, 2, 3, he's now at 6. But if he was at 10, he's a 1, 2, 3, he's now at a 3. So this was a nice, easy way for me to get rid of the loops. Yeah, and the only other important thing in here is I'm going to pass in, now it's going to be player two's turn, and I'm going to pass in my multiplier. So this multiplier was the same thing that Alex ended up using too, where we had 1, 3, 6, 7, 6, 3, 1, based on the probability. And I figured these out just by using some paper and writing out all the different possibilities. So yeah, that's what we do if it's player one's turn. If it's player two's turn, we do the same thing, but we pass, now player one's score is not going to change, but player one's position is not going to change. Player two's score is now going to be, oh, sorry. If it's player two's turn, then player one's score has now been updated. But player one's position and player two's score do not change. But player two's position on the board is now new. So he's going to get his new position on the board based on where he lands on the board. And we're going to pass in player one because it's now his turn and the multiplier. So now in order to call my initial function here, I'm calling it in with my initial input. So player one's score is going to start at 0. His position is going to start at 10. And for player two, I had to set his score to negative, the negative of his position, because I'm going to increase his score at the very beginning of round one. So his score starts out as negative, but it's going to increase to 0 as soon as player one starts his turn. And we're going to start him on position 4, and it's player one's turn. And right now, since I haven't called anything yet, my initial multiplier is going to be 1. So every time we branch out, we're just going to keep track of the multipliers and add that multiplier to the number of wins that each player wins. So at the end, I'm going to get the total number of wins for player one and number two. So I'm just going to print out the maximum value of those. And for me, it ended up being player one won 190 trillion times. And player two was a big loser. He only won 90 million times.
It's like 90.
Sorry, 90 trillion, 90 trillion. 90 trillion and 190 trillion.
Cool.
Did anyone have player two winning? I just wonder. It seems like player one always has a big advantage by going first. So I just wonder, there must be some board positions where player two could win.
I don't even know which one on mine won. I can. So.
I think mine has player two winning.
Oh, really?
Yeah, 5, 6, yeah.
What were your starting positions?
5, 6, and 1.
6
and 1.
Let me move you guys. Let's see. Oh yeah, you had player 2 winning. Ooh, it was close for you, it looks like. Can you see my results here?
Yeah, I can see.
Yeah, it looks like player 1 and player 2 are really pretty close. Is this what you got for your final answer?
Yeah.
What are your results?
Can you see them in my console?
No.
You can
Oh,
shrink
I see.
the.
That's on the right
Yeah, you
side.
can-
My
Yeah, on the right side here.
screen's
I'm
cut.
printing.
Okay.
Player 1 wins and player 2 wins. That was for Farouk. Mine was. Get back here. Yeah, mine was much bigger difference between player 1 wins and player 2 wins. Cool. Yeah, that one took some thinking to get through part 2.
It was hard for me actually. I had a lot. Even on paper, I was getting lost to imply this logic.
It took me a while to figure it out, yeah.
Just repeated optimizing until you get something that runs where you don't have to like run it overnight.
Yeah.
All right.
That's that.
That's that. Any other questions so far?
Alex also completed all 25, I saw. Congratulations.
Yeah, congrats, Alex.
Yay.
I guess we'll see you 22 next time.
See what?
You're day 22. That was your final one that you just finished, right?
Oh, yeah. Wasn't as bad as I thought it was going to be, but yeah, it was more not wanting to do it.
Understandable.
And then I was like, yeah, might as well just get around to it. And I think I'm gonna probably try to go back, and I'm in the process of finishing up 2015 as well.
Oh, wow.
But then we'll see how far I get. I think I only have a couple days left now. I finished, I think I started a little bit about halfway, so should be able to finish it up in the next week or 2.
Is that the last year you have to finish?
Oh no, I've I think 3 more years to finish. I have
Oh.
1 year that I realized I didn't even start. 2019, I didn't even start, so I got another fresh one to do if I want to at some point.
I still need to try to code day 23 and 24.
Oh, that's right.
I got the answers, but I didn't code anything for them.
Yeah.
Even 24?
Yeah, 24. We used Excel, baby.
Excel, I actually tried 24 with code, but it was not completed yet.
You're not gonna get the code unless you spend a long time analyzing the data first. I think 24 I can code quite quickly now that I know how the problem works. You really gotta.
You know the pattern, because
Yeah.
you needed to realize the pattern of how our machine works, right?
Yeah, you gotta really inspect it line by line and figure out what's happening.
There are people who reverse the math.
Ooh.
I got maybe like 3/4 of the way there, but I couldn't fully reverse it. But I did find some people online who reversed it. That was really impressive. So I'm trying to go backwards myself. So I'm analyzing some of the ways that other people have done it. I found one version in Python that did the math in reverse, and I can't quite understand about 1/4 of how they ended up doing the reversal. So, but I didn't do it with the math. I mean, I tried to do it with the math, but like I said, I couldn't get it with the math, so I ended up just doing it with patterns.
Maybe I'll try tonight to code that one.
Earlier years, same difficulty as this one, like 2019.
I think there might only be like 1 or 2 question difference between the years, but I thought this year, like not having done 2019, but I did 2020. 2020, I want to say there was about maybe only 3 or maybe 4 questions at which I just skipped over B and it came back to B parts later. Whereas I want to say for this year's, I probably skipped the B of about 5 questions, maybe 6 even, and then came back to finish it later. So it kind of suggests to me that maybe that this year's was a little bit harder, at least for me. But I mean, 1 or 2 can also just be part of standard deviation. So you can't really definitively say whether it was harder or not.
Also depends on question type, because a lot of the years have completely different question types. Like I know there was one year they had like the int code or something that a lot of people got stumped on, and then it reused that same type of question like 3 times throughout the year.
There was one, a couple of years where they've had like early on in the series, you answered a question which then fed into another question in the future.
Yeah,
this year all the questions were fed. But you know, in that kind of case, you kind of have to finish an older one before you move on to the later ones. But yeah, so in that sense, you know, it was a little bit easier, I guess, for some people. But I don't know. I still had fun. I mean, so it's hard to say. You will know next year when you have the sample size of 2. And the year after that, with a sample size of 3.
Well, we can always do previous years until before then.
Yeah, it's true. You can go back and do the previous years. They're all
I was thinking same, but if they are same difficult, I think I need some break in between. Like
I think I'm going to enjoy sleeping at night.
Yeah, so take some break and improve Python knowledge a little bit more, me, and then try to attack them or tackle them. Because now if I go back like this, I will not have time to learn them well.
Yeah. So. Or do like the first 10, 15 days of every year. And then save the last 10 days for times when you have a chunk of time that you really want to chew away.
I'm actually interested in the hard ones, they seem to be the ones who will teach something.
Yeah. Day 1 is boring.
Yeah, this one's actually some challenging, but they also require time. For me, at least, they take a lot of trial and error, So yeah.
Of course. All righty. Well, we're closing in on 2 hours again, so let's say our goodbyes, and we'll meet back up again on Wednesday to go on to 22 and 23.
Yeah. Same bat time, same bat channel.
What's that?
Same bat time, same bat channel.
Exactly. All right. Anyways, see you guys later.
Take care, guys.
Bye.